Good morning. How many of you are lazy this morning? All right, that's good. I'm in the right group. Excellent. Well, I want to talk about getting lazy. My name is Venkat Subramaniam. Thanks for coming. When we hear about functional programming, we often hear people talk about immutability, for example, and various other things I won't even mention. But I find that a lot of those things are really means to the end. What we really are after is efficiency in coding. Well, of course, expressiveness of code is also very important, and functional programming gives us that once we get familiar with functional style of programming. But one of the real big benefits, I think, really is lazy evaluation. So that's what I want to focus on today, talk about how we can actually, what is lazy evaluation and how we can actually benefit from that. I'll give examples from a few different languages here. I'll give a few examples in Java, a few examples in C#, a little bit touch on Scala, and just a little bit on Haskell as well. So those are the four languages I'll touch on to various degrees, depending on what we want to do. Best time to ask questions or make comments is when you have it, so please don't wait till the end or hesitate. Anytime is a great time. Questions, comments, anything you want to talk about, draw my attention. I'll be more than happy to listen to you. As you have noticed already, I don't use slides. I hate using slides. I'm going to just rant off, answer questions if you have any, write some code, and just have some fun. So let's get started. So what does it really mean to be lazy? What does lazy evaluation really mean? Well, lazy evaluation simply differs from the so-called eager evaluation. So normally when a computation comes across, a system can decide to do it right away, which is eager evaluation, or it can decide to postpone it. Well, benefit of postponing it is we could do four things with a postponed operation. First, when you give me a computation, I can do it right away, which is eager, of course, or I can delay it to the point where I don't have to run it at all. And of course, both in life and computing, the efficiency comes from not doing stuff that we don't have to do. So we postpone it until the point where maybe we don't have to evaluate this and we can just simply not evaluate an operation. Or we can pass an operation along to yet another entity which can decide to do whatever it wants to do with it. Or of course, we could then eventually evaluate it, but minimally to get the results we want and not really execute it eagerly to the fullest extent. Well, let's talk about that a little bit further, but I want to talk about something else that we have in computer programming, but a lot of us don't really experience it. This is one of the aha moments for me over the past about 30 years I've been programming, and that is I used to read a lot about stuff back in the 80s, and I would like to sit there and say, wow, this is amazing, wish I could try this. And it's excitement really to me today is I can actually try the stuff that I once were only able to read because of the, so to say, democratization of programming world. We got a lot of things available to us, much more easily available without having to really go to a, bigger corporation or a university to get access to things. We can just have them available to us on our own laptops and devices. Well, one of the things I want to talk about today is applicative versus normal order. Well, most of us program in mainstream languages which only support, unfortunately, the so-called applicative order. Normal order is actually quite abnormal in a lot of ways. So let's talk about that with a little example to see what that really means in this context. So let's take a little example to play with it. So let's say we have a little function here. Let's keep it extremely simple. I got a function called compute, and the function compute, of course, is going to take a number. And let's keep it extremely simple, returns just the double of the number. But of course, within this, I'm going to simply say called, so we can actually see that this function actually was called. But of course, I'm going to go back here and say int, let's say x equals to 4. And then I say if x is greater than 5 and compute of, let's say, 5 is greater than 10, then I want to go ahead and say, for example, in this case, we'll simply output here. Let's call this as result, otherwise we'll say else, really silly, but we'll call this as no result. So if you notice this, we have a little code where if x is greater than 5, then I call compute, and then of course I print out result or I print out no result. But when I run this code, of course, everybody in this room knows that when I run this code, the compute method was absolutely not called. Well, why was compute not called at all? Does anybody know the reason for it? Come on, don't be shy. Thank you very much. John McCarthy created this concept of short-circuiting way long time ago in the 1950s. And everyone programming knows about short-circuiting. In fact, that's kind of normal for us to expect short-circuiting. There's no surprise at all. We program knowing short-circuiting very clearly. On the other hand, if I say temp is greater than 10, and I'm going to say int temp equals compute, well, the question for you now is, will compute be called? Yeah, we said yes. Should compute be called? No, right? So this is when your feelings differ from what the language thinks it should do. When you disagree with the language, guess who wins? The language, of course, right? Which is the sad part. But of course, in this case, when you run the code, it is going to go ahead and call the compute method. There's no doubt about it. And of course, in this case, the compute, of course, is going to return the value. But sadly, the compute was called, even though you and I know very clearly the result of compute is not going to be used. An example of eager evaluation, but more so an applicative order. But it doesn't have to be this way. It is just this way in a lot of languages we use in the mainstream. But let's take this example a little further just to play with it. Now let's take an example here in Haskell for a minute. I'm going to create a function over here called add a and b equals a plus b. And of course, I'm going to call a function called evaluate, let's say value equals value. And then I say main equals, and I'm going to print evaluate, and then I'm going to call add over here in 1 and 2. Now, when I run this code, of course, what you can see is it printed 3. That's not the most interesting part in this code. But let's talk about the order of evaluation here for a minute. Well, in languages like Java and C# and a lot of mainstream languages, when will add be called? Well, add will be called right away when you see the add being called over here. The evaluation is instantaneous. It's eager. It's also known as applicative order. So the word applicative order is just the order in which it is applied. Well, add is applied, then evaluate is applied. Apply is a very fancy word for invoke or called. So when add is called, it gets called or evaluated. Well, but Haskell is very different in that regard in the terms of how it's going to do this stuff. So most languages we use in mainstream use applicative order, but some languages actually use normal order, which is quite abnormal, like I mentioned. Let's go to this example. I want to show to you that add is not being called right away. Add is actually evaluated pretty lazily. So when you go to Haskell and say, hey, call add, Haskell says, why? Because I want to pass it to evaluate. So you need to call evaluate too. And it says, but why? Well, I want to pass it to print. Okay, that's a good reason, because print is going to show the result. Humans will see it. I better do this work. So it's going to postpone until the point where it cannot postpone anymore. But how do I prove it? Well, unfortunately, I cannot put a print statement in language like Haskell to prove it, because print statements are impure operations. Haskell wouldn't allow me to put it in arbitrary places. So I was scratching my head, how do I prove that this is how this works? And I never thought I would actually use this debugger to make a point, but that's exactly what I'm going to do here, is to kind of step through the code. So I'm going to go here and call GHCI, which is the REPL or interpretive evaluator for Haskell. And I'm going to go ahead and load, in this case, the sample.hs file. Well, now that I've loaded it, I'm going to put a breakpoint, but I'm going to put a breakpoint right here on line number 1, character number 16, as it turns out to be. So I'm going to go back here and say break at 1 and 16. So I've entered a breakpoint. Now I'm going to go ahead and call the main function. Well, you can see that the main has stopped right here on line number 1, and it tells you that it's waiting for you to continue. And I'm going to, of course, say continue right now, and you can see the result of 3. Well, that proved the point that add was actually called, which is kind of pointless because, of course, we know the add was called. But what's really exciting is I'm going to go back to this code and change it to 42. Now take a look at what this code is doing. When I run the code, of course, the result was 42. But the beauty is you go to Haskell and say, Haskell, call the add function. And Haskell says, but why? Because I want to pass it to evaluate. Why are you calling evaluate? Because I want to send it to print. Well, gosh, then let's go ahead and call evaluate first. You come into evaluate, you return the 42, you never actually used value, and Haskell says, why bother then? I'm not going to really spend my effort running the add method or add function because there is no value in running it. Well, is that really true? Well, to prove the point, again, I'm going to go back to the REPL. I'm going to load up the function one more time, the file, So it's loaded up. I put a breakpoint again, exactly in the same line of code as we did a minute ago. I'm going to go ahead and call the main function this time, but notice it never hit the breakpoint. It actually went right through and printed 42, a proof that add was never actually evaluated. Well, that's normal order right there, as we saw. So essentially, Haskell says, I don't have to be evaluating stuff unless otherwise I really need an evaluation. This is a very normal sequence in language like Haskell. But the first question, of course, obviously is, why can other languages like Java and C# do this? Why does Haskell do this differently? And the reason is actually extremely simple. And the reason is, in Haskell, almost everything we create is pure. So when we talk about immutability and purity in functional languages, it's important for us to understand why purity is so important. Because if we don't understand that, to me, purity or immutability is like vegetables. You don't go to children and say, you have to eat vegetables. Nobody likes that. So we got to give a good reason why this is important. There's got to be a motivation to do it. And the real motivation is, if a language does not guarantee purity of a function, well, it's got to then eagerly evaluate it. Languages like, this is really funny when you really look at languages. Think about defaults. Languages like C# and Java fall on unsafe defaults. Languages like Haskell fall on safe defaults. By definition, the default in languages like Java and C# is mutability. Whereas by definition, the defaults in languages like Haskell is immutability. So when you define a function in Haskell, it is pure by definition. And if you want it to be impure, you have to plead with the language. You got to say, please, please, just this one function, give me permission to make it impure. Whereas in languages like Java and C#, you got to plead with the language for purity, because by default, those languages promote immutability. Well, because things are immutable, if something is not being called, when function can have side effects, if the function is not called, you're going to really be surprised in languages. In fact, you may ask the question, wait a minute, if that is really true, why doesn't C# and Java call the function when it's short-circuited, but why do they call it when I assign to a temporary variable? And the short answer to that question is language specs. And language specs rule. So, in fact, if you read the language spec, for example, C++, the language spec actually clearly says, even if your constructor were to perform a side effect, the language compiler may opt not to call your constructor. So same way, language specifications clearly say, even if a function were to have a side effect, a short-circuiting will reject the function call and may not perform it. But language specifications do not apply that rule in various other cases, and that's the reason why the languages don't optimize so easily. But let's take that a little further and see how this could actually be benefited with a few exceptions, if you will. So to understand that, let's take this example we just saw here of the compute method. But I'm going to write this example again here, but in the case in Scala for a minute. So I'm going to say over here, define compute. And in this case, of course, I'm going to say number, given a number, which is, let's call this as integer, if you will. And then I'm going to simply say, go ahead and say a printout, let's say called. And then, of course, return number times 2, just like what I did in Java. But in this case, of course, I'm going to say x equals 4. If x is greater than, let's say, 5 and compute of, let's say, 5 is greater than 10, I want to print out, let's say, in this case, result. And then, of course, print out else will simply say no result. Just example, what I did in Java, I'm just repeating that here in Scala. Well, as you can see in this little example, you saw the no result. Clearly, compute was not actually called. But what if I take this compute right here and assign it to a variable called temp over here, and then assign it to a compute, and then, of course, run the code? Well, when I run this code, of course, what you see is, unfortunately, Scala called compute as well. Why? Because languages like Scala and F# are what I call as hybrid languages. They promote immutability, but they don't guarantee immutability at the language level. So as a result, they still have to evaluate things. Well, how do we really get around that? Well, Scala says, you could have a side effect in compute. I don't have a way to guarantee that. And if I don't call it, you're going to be surprised about it. Well, you can have a little discussion with the language and say, hey, language compiler, I know what I'm doing here, so give me a little break here. Well, that break comes from the word lazy, if you will. So notice right now when I run the code, Scala did not evaluate the compute method because I annotated the variable with the word lazy. This is very similar to what you can do in F# as well. You can give a little annotation to the language to say, this one you can be lazy about it, and even if it were to have a side effect, I'm not going to be offended if you don't call it. So the language says, all right, I'll ease up on the eagerness over here, and I'll postpone the evaluation until I cannot avoid the call to it. But of course, in this case, as you can see, if x were greater than 2 and I run the code, you can see that it actually called it because in this case, the value of temp is needed. But if the value is, let's say, greater than 5 in this case, you can see it bypass the call. Well, that brings up the question, gosh, how do I do this in languages like Java and C#? Short answer in Java, good luck, there is no way to do this. Well, C# makes it a little bit easier if you want to do something like that. I'm going to just grab this function here from Java, if you don't mind, and bring it over here to C#. So right here is the compute method. And you know how to go from Java to C#, right? Just convert methods to uppercase, you got almost the code you want. Well, so here I have a code here in C#. The compute method takes a number and returns a double of that. And of course, in this case, I want to print that out. So we'll simply say, here's the console write line. I'm going to simply say called right here. But I come back here and say int temp is equal to 4, actually x equal to 4, and I'm going to say if x is greater than 5 and compute, and I'm going to say this compute method takes a value, let's say 5, is greater than 10, let's say, and again I want to say result, and of course else I want to simply say in this case no result. Well, what does C# do? Well, clearly in this case, you can see it said no result. Didn't eagerly call the method, short-circuiting at work. But what if I were to take this one again, but this time I'm going to say temp over here, and I say temp is equal to compute 5, and you can see that C# is being eager, just like Scala and Java were. But in the case of C#, what you could do is again annotate it by saying lazy int, for example, and you can, of course, define it as lazy. But that brings up the question, how do I really make things lazy in languages like Java and C#? Well, this is where a little bit of a charm comes in. I'm not completed with the C# code yet, but I need one more minute before I can do that, so I'll come back to that. So some languages are born lazy. They were born at the beach. They were sitting there and doing absolutely nothing useful when they were born, right? So some languages are born lazy from the get-go. But some languages have to work really hard to be lazy. Some languages are like me. I'm always hyperactive, trying to do stuff. And my wife would tell me some days, why don't you just sit down and relax? I'm like, how do you do that? Well, that's the way some languages are. They're just eager, and you got to work a little extra hard if you want to make them lazy. So we talked about the eager versus lazy, but how do you really bring lazy evaluation to some of these languages? How do you postpone these evaluations? Well, this is where the charm of lambda expressions come in. So what do lambda expressions do? Well, lambda expressions really are anonymous functions. So you can create a function, but one of the really nice things about creating functions as lambdas is you can pass functions around. So a function can now receive other functions. You can create functions within functions as lambdas, and you can also return functions or lambdas from other functions too. We, of course, call them as higher order functions. So what does this give us a benefit with? The benefit you get out of this is now you can pass functions around, but what is the benefit of passing functions around? Imagine I have a function. I want to say, here is a function. I'm going to give it to you. Well, what would you do when you receive something on your hand? There are 3 things you could do. You could use it right away. If I were to give you an apple, for example, you could eat the apple right away. Or you can postpone, be lazy about it, and you can eat the apple later on. You could throw it into a trash can and say, I don't want to eat this apple. Or you could give it to somebody else and say, here you go, I got this apple, but I want to give it to you. And that person in turn can do one of those 4 things. Give it to somebody else, eat it, discard it, or eat it later. So the point really is, when we pass functions around, we can either be lazy or eager or evaluate it right now or discard it. And so this gives an opportunity for us. And that's exactly what languages like C# do. So notice what I'm going to do here. I'm going to say a new, and I'm going to create a lazy over here. So this becomes a lazy of int, but I'm going to wrap this into a little lambda expression, if you will. And of course, in this case, you can see that I've just done a little bit of postponing in here. And of course, in this case, I say temp.value is greater than 10, and I'm going to evaluate it. But notice the laziness in this case. C# did not evaluate the compute function. Why? Because the compute is wrapped into a lambda, and the lambda doesn't have to be evaluated right away. The lazy object says, thanks for giving this to me, but I will wait until I see what happens. Now, of course, in this case, if I say x is greater than 2 and run the code, you can see that it did call it because the value was, after all, needed. But when did this evaluation actually happen? Well, to prove that, if I say here over here, you can see that here was actually called, and then much later was the called function evaluated. That is the laziness of the evaluation, as you can see. So in other words, we can use laziness to really make advantage of this. If you're programming in Java, unfortunately, lazy is not available, but nothing stops from creating one yourself if you want to, and you would use a supplier to do this in language like Java. The code I've highlighted here in C# is equivalent to what's called a supplier in Java, and you can get to use that pretty much to implement the same idea if you're interested in doing. So we can see how laziness comes into picture right there. But I want to take this further and say, what can we benefit from when it comes to lazy evaluation? And to understand that, I want to take yet another example and play with it. I'm going to use this example in Java, but you could use that in any other language. But a quick show of hands, I could use either one. How many of you program in Java here? A few hands. How many of you in C#? I'm sorry, you know who wins here. Okay, so we'll just use the C# example in that case. So I'm going to use, I'll come back and show you another example of Java a little later on, but for now we'll use a C# example. So to prove a point here, I want to take this little example, and I want to say in this case, well, what do I want to do? Let's say we start with a list of numbers to begin with. So I'm going to say int over here, we'll call it numbers equals, and in this case, I'll say new list of int again. Well, in this case, let's define a few numbers. Let's say 1, 2, 3, but notice I put a 5 and then a 4. Change the order here intentionally. And then I'm going to say 6, 7, 8, and this potentially could go on to 1 million values, let's say. It doesn't really matter. But I want to say, find the double of the first number greater than 3 and is even. Well, I want to perform this operation. So how would I do this in a language which is imperative in nature? Let's start with a little example. I'm going to say result is equal to 0 to begin with. I want to print the result. You can pretty much do this example in Java, much like what I show you here, not very different at all. So you can try it out in either of those languages. So in this case, of course, I'm going to say for each, of course, I'm going to say var, and I'm going to say element and coming from in numbers. And of course, I want to loop through these numbers and get the result out of it. But how do I get the result? I'm going to say e is greater than 3 and e mod 2 is equal to 0. Well, then what do? I'm going to say result is equal to element times 2 and do a break operation out of it. Well, we all know what this style of programming is. It's an imperative style of programming. But imperative style of programming involves mutability often. It also is very verbose. It's something we have done for a long time, but it's tedious and it's a lot of work for us to do. I'm going to also say that imperative style of programming often has accidental complexity baked into it. It's often error-prone as well. I could do this a lot better in functional style of programming. Let's see how we can do that here in C#. So what I'm going to do in this example is repeat this, but this time I'm going to say, well, numbers start, and I'm going to say where, given an element, I want to say e is greater than 3. I mean, of course, I could have really said e is greater than 3. I could have done that here, but I'm going to instead call e is greater than 3 as a function. Then I'm going to say where and I'm going to say is even, a second function I want to call. Then I'm going to say select, and I'll call it as double it. And then finally, in this case, I will simply say, oh, what do I want to do? The first number, of course, I'll call first right here and ask for the result out of it. Well, of course, I need these little functions to make this work, so let's get that going. So public static Boolean is greater than 3. Well, that should be fairly easy to do. What does that do? Well, it takes a number, of course, and all I'm going to do here is simply say return number is greater than 3. Well, let's go ahead and quickly write those other two functions I would need. This, of course, is even, and all that it is doing is mod 2 is equal to 0. And finally, this is going to become a doublet, and all that the doublet function does is simply return back, let's say, number times 2, and returns the double of that particular number. Well, when we run this little code, you can see the result of that is also 8, so that's a functional style code. Now, clearly, some of the benefits you see up here. If you take this code and ask somebody what this code is doing, what are they going to do? They're going to have to look up and down. In fact, this is the beauty. Put a imperative style code in front of somebody, but then sit in front of them and watch their eyeball movement. It does this, right? And it goes up and down, and then it does this. That point is called the point of confusion, because they're like, what does this code really do right now? Well, the beauty of the code in the bottom is it's a single pass through the code. Given all the numbers that have been given to me, get me only the numbers greater than 3. Now get me only the even numbers. Double them, get the first one. What a relief, isn't it? It's a single pass through. You go from the top to the bottom. The code begins to read like a problem statement. I was working with a company in the north part of the US, and I don't know anything about what they do. I was there to just do a training course I was offering. But one of the developers said, would you please take a look at my code and comment about it? Usually I get scared when people do that, because when I can't understand most of their code if it's not written very well. But I look at the code and immediately was a relief, because whoa, I could actually understand this code, because the code was pretty much doing what you see up here. It's got ships coming in. It says, well, all the ships we are dealing with, we want only ships that are arriving, and one from the international destination, and one with this kind of cargo. And I'm like going through this top down, and I'm reading through the code, and I'm understanding it. I'm like, wow, even I could understand your code. What's up with this, right? And that's one of the benefits, is that the code is actually easy to read, easy to express. But that begs the question, oh my gosh, what about performance? Well, be careful about this, though. If you're programming in languages like Ruby or other languages, this might not give you a good performance if you're not very careful about it. But languages like C# and Java have done a really wonderful job. This is why I really appreciate these languages. They didn't just bring in the concept and say, good luck with it. They actually took the time to do a really good job with it. Let's see what that is in a second. Let's go back to this code here, but I want to remind you about the sequence we are working with. 1, 2, 3, 5, 4. So what is the number of effort units of work we do in the imperative code? Well, let's take a look. I've got this collection on my hand. E is 1 to begin with. Well, 1 is greater than 3, no. 2 is greater than 3, no. 3 is greater than 3, no. 5 is greater than 3, yes, of course. Is 5 even? Well, no. Is 4 greater than 3? Yes. Is 4 even? Yes. Double 4, wow, that was 8 computations we performed. So the total cost of this was 8 units of work. That's what we did. So 8 units of work in imperative code. Not all units the same, but that's good enough for our purposes here. So in the imperative style, we did 8 units of work. Let's look at this code naively for a minute. Given a collection of 10 numbers, I had to ask if every given number is greater than 3. That's what? 10 operations. Dead on arrival, because 10 already is greater than 8. But to add insult to injury, then we take 7 values and see if they are even. 10 plus 7, 17 computations. Then we double 3 of the values. 17 plus 3, 4 values off by 1 error. Well, that's 21 computations. Wow, 21 units of work. So this looks like 21 units of work compared to, let's say, 8 units of work. But if you really wanted to make this worse, just add a few more values to the end over here, while the imperative style code is sitting there and saying, no worries, your functional code is going to do a lot more work. That doesn't look really that appealing, isn't it? Well, here comes the good news. I forgot to mention one little thing about these kinds of functions. And I've only seen these capability among my own children and functional style code. They both are lazy to the bone. In fact, I'll give you a little scenario I've seen at my home a lot because that really resonates well with this. My wonderful wife often has to talk to my children when I'm away, and I got teenagers. Well, if you have teenagers, you know what I'm talking about. Or if you have been a teenager once, you would know what I'm talking about. Well, teenagers are fundamentally lazy, as you know. So my wonderful wife will tell my teenage son, hey, turn off the TV. It's like no words were spoken because nothing happens in the house. And she kind of looks at him and is like, well, I told him to turn on the TV, nothing happened. Then she says, go put the trash out. No muzzle was actually moved. Then she says, do your homework. Nothing really happened. Then she says, I'm calling daddy, and everything works. Well, they could have renamed the first as call daddy. That would have worked really well, in my opinion. Or call mommy in some families, depending on the house. But the point really is, these are what are called terminal operations. In other words, when you go to the list and say where, it says, yeah, okay, thank you for asking me to do that, but maybe I'll do it, maybe I won't do it. Where again? Select, maybe. First, oh dear, let me get to work because the result is needed after all. Well, let's actually see if that's true. So to prove that, I'm going to go back to this code right here, and I'm going to go ahead and say output, and I'm going to say is greater than GT called with, and then let's go ahead and say 0 here, and then let's put number. Similarly, I'm going to go ahead and output, let's put is even right here. And then, of course, finally, we'll call this as double it. Now, before I run this code, let's go back and see how this is going to be evaluated. Well, this function does not, let me tell you what it doesn't do. It does not evaluate that particular function is greater than 3 for all the elements in the list. Instead, what it actually does is it takes these 3 and does what's called fusing. It just mushes them together into one function, if you will, because it's all lazy functions, and puts it together and says, here we go, and it runs that fused function per element, but only to the extent how much it's needed. So in other words, it takes 1 and says, hey, 1, are you greater than 3? And 1 says, oops, not, and it bails out, gets out of there. So does 2 and 3. Well, then comes along 5, and 5 says, of course I'm greater than 3, but 5 escapes at this particular point. 4 comes along, 4 is greater than 3, 4 is even. We double the 4, and first says, oh, thanks. And the entire mechanism says, oh, we're done then. No need to touch 6 and values after that. And so when I run this code, you can see the output, exactly 8 units of work. One more time, we evaluated 1, 2, 3, 5, and 4, but we never ever touched 6 after all, because that is lazy evaluation at work. So lazy evaluation gives efficiency in code. So even though this code looked really expressive and beautiful, we have often concern about performance, but be rest assured, with lazy evaluation, we don't have to worry about it because it doesn't do the work until it no longer can avoid doing the work. Just because we have a functional style of code, don't assume that this is available. Not all languages are created equal. This is an example in C#. So is an example in Java. If I create a very similar example, you will see Java doing the same thing. Both Java and C# also have embraced this efficiency. You can again see the specification being different here. Even if these functions were to have side effect, they may not be called after all. Well, that brings up the point. If you're interested in using functional style, it's important for us to avoid side effects in our code. In other words, make functions pure, because those functions may never get evaluated, and we should be very careful about impurity of operations. So all the talk about immutability and impurity have a really bigger end to it, which is lazy evaluation and efficiency that we really are after. So we can see the benefit of laziness here in this code, as you can see, and it decides not to evaluate this function until it no longer can postpone it. That's one of the biggest benefits you got out of it. So that laziness gives us the benefit of having to really postpone operations, if you will. So as a result, in this case, you don't have to worry about running computations that don't have to be run. That is one of the biggest benefits you get out of laziness. Lazy evaluations has the performance implications. But, okay, so we can have laziness in code, that's great, but can we benefit from laziness moving forward to a bigger degree? And once, this is the beauty of things. One thing leads to the next thing. And generally speaking, every single step may be really small, but the minute you have taken 5 or 6 or 7 steps, and then you take a few more steps, you suddenly feel that you're on a different floor than you were in. And that's one of the biggest benefits, is you keep adding on to these benefits. So in the beginning, we are saying, make sure functions are pure. Well, make sure you honor immutability. Make sure functions are pure. Make sure functions don't have side effect. Well, what is the benefit that gives you? Several benefits, just one of them being that you can have laziness. But now that we can have laziness, what's the benefit of that? Well, one benefit is, of course, efficiency of code, but there is yet another benefit, and that is you can start bringing in evaluations which are related to infinite streams. What is an infinite stream? For this, I'll give you an example here in Java, but you can write an example in C# as well. I'll maybe convert this to C# and show you in just a few minutes. But what is infinite streams? Well, an infinite stream absolutely has no bounds to it. So I'm going to say stream.iterate, and I'm going to say here is 1 comma, given an element plus 1. What does this do? Well, it says, this is Java example, as you can see. It says I'm going to start with 1, then I'm going to go to 2, 3, 4, 5, and keep on going. Well, how long can the stream go? Well, there is absolutely no limit. It's infinite in size. I know what you're wondering. You're saying if it's infinite in size, where in the world would you store it? On the cloud, of course. You're just kidding. So the point really is, it's infinite. But how could you potentially have an infinite stream? The answer is laziness. So this lambda will not be evaluated until it really is needed, and that is the beauty of lazy evaluation. Well, laziness gives an ability for us to have things like infinite streams. You can tell it how many elements you want, and it'll evaluate it on demand when you actually ask for it. And if you don't ask for it, it's not going to do the work to get you that. Well, what's the benefit of using something like this? Well, let's go ahead and take a look at how we could benefit from this in terms of getting something really powerful and easy to work with. Well, now you have an initial value, and you have a generator that's going to generate subsequent values for you, and we can leverage on this idea really nicely. Well, to understand this, let's take a little example. Let's say given a number, let's say n and k, well, given numbers, let's say n and k, let's say compute the square root of let's say first k even numbers starting from, let's say, n. Well, compute the total of square root of k even numbers starting from n. Well, seems like a very simple problem to do. Compute the square root, total of the square root of first k even numbers starting from n. So let's go ahead and say compute, and I'll say n and k. Well, what in the world is n? Let's give a random number, 72 to begin with. And I want to give another value for k, which is another random number, 219, let's say. Well, I want to perform this operation and get the result out of it. So how would I go about doing this work? Well, I'm going to say, in this case, compute, let's say, double, and we'll call compute n comma k. And of course, these are going to be simple values to pass in. What am I going to do? Well, let's say int index is equal to n to begin with. After all, we need to work with an index value, don't we? Well, then I'm going to say count equal to 0. We absolutely need a count. Then I say double result is equal to 0. And then finally, I'm going to return the result when we are done. What did we do so far? Really no useful work after all, right? All we did was we defined some variables, and it's a good time to take a coffee break, and so it was a lot of hard work, right? Well, the point is, in imperative style code, we create a lot of these things called garbage variables. Garbage variables are variables simply there to provide our code some points to store data, but they don't have any really good purpose at all in the code. Then I'm going to say while count is less than k, and what do you normally do? It's a ritual, isn't it? You stop and you ask the question, is it less than or equal to? Do you ever ask this question? Every single day, isn't it? In fact, it's code like this that makes us feel really stupid, right? Because you look at that code and you say, is it less than or equal to? You're trying really hard to reason it. And then you leave the computer and you stop by the door. Was it really less than? And you're eating food at dinner, and the family says, are you okay? Yeah, I'm fine. You look really pensive. No, I'm thinking, is it less than or equal to? I forgot at work, right? Oh, it's always this thread that goes along. You're not sure ever, right? These are code that's really hard to reason. We have to think very carefully to know what this code really means. Then what do? Then you say, well, if it's even after all, so I'm going to say if the index is mod 2 is equal to 0, yay, we have a value that is even. So what do I do now? I'm going to say over here, result plus equal to math dot square root, and then of course I'm going to take the index value and compute the math out of it. Are we done? Well, you're going to say, no, we're not done. We need to increment the index value. Well, okay, so here is index plus plus. Are we done? Oh, no, not really. You got to increment the count value. So count plus plus. Are we done? What do you think? Is it correct? No, what's missing? The plus plus has to be outside. Okay, let's move it outside. Is it correct now? You're like, no. One of them has to be inside. One has to be outside. Well, which one then? Well, index has to be outside, but count has to be inside. Is it correct now? You're not sure anymore, right? That's the beauty of imperative style code. You're never sure about it. You're sitting there and thinking deeply to reason it. And then, of course, you're like, I think it is correct, right? And then you're trying to run through that and see what the result is to see what the code is going to provide as a response. Well, of course, in this case, I'll mark it as static function. And, of course, it gave us some result, but God knows if it's correct. Well, but how do we do this code in more of a functional style? Well, thanks to lazy evaluation and infinite stream, let's see how this is going to become a lot easier to work with. So I'm going to comment this code out, but re-implement it in a functional style. So here we go. So what am I going to do? Return stream.iterate, and I'm going to say iterate. What am I going to do? Starting with the number n, and then k, while given an element plus 1, there is your infinite stream that you have with you. Now, what does the stream do? I'm going to start with n, and I'm going to keep on going. N plus 1, n plus 2, n plus 3, and it keeps going. Well, what's the next thing? Filter. And what am I going to do with this filter? Well, given an element, I'm going to say element mod 2 is equal to 0. Well, give me only the even numbers. Well, okay, great. What's my next operation? Map this value. Given an element, return math.square root of that value. So we performed what we did on line 18 and line number 19. We took care of those two lines. But then how do we go? How much do we go? Limit to what? K values. Is it less than k? Is it less than or equal to k? It's k, damn it, keep moving. You don't have to waste your time on it, right? And that's the beauty of this, is simply you have this filter, a map, and of course limit. And what's the last step? We want to perform a sum operation. And of course, in this case, I'm going to perform a sum and get the result out of this particular function. So when I run this code, of course, it says I want a stream. So let's go ahead and implement a stream right here. Bring in the stream.stream. So now that I have the stream on my hand, what am I going to do now? Well, run the code, and you can see the difference. Not only is the code concise, the code is extremely expressive as well, as you can see right here. So what's the benefit? The benefit is You're not really dealing with accidental complexity in the code. You're not sitting there and struggling with garbage variables. You're not struggling with less than or equal to. You're not dealing with control variables. The code becomes extremely simple to deal with. If you have the code in the top, and you're looking at that code, struggling to understand what the code is doing, when a business analyst comes to you and says, hey, what does this code do? Your response normally is, that's what I'm trying to figure out, you shut up. Because you're really angry dealing with the code. Whereas in the code in the bottom, well, you can actually discuss with somebody and say, that's what the code is doing. Does that really make sense to you? Because the code begins to resemble the problem statement. But of course, in this case, lazy evaluation plays a very vital role because without laziness, absolutely you cannot do this. So lazy evaluation is critical. Let's see how we can. This is, of course, in Java. Well, in C#, of course, C# was influenced greatly by LINQ, so the functions don't look like filter and map, but there are very equivalent functions to do. How would this look like in the case of C#? Well, let's take a look at that really quickly to see how we would probably implement something like that potentially here. So let's get this back to rolling. Well, of course, I want the math and the square root. Well, before I do that, really quickly here, you could actually do a little bit of simplification here in Java as well, using what are called method references, and that can minimize a little bit of noise in the code, if you will. Just a few little benefits. Similarly, if you had that other function available separately, you could just use a method reference for it also. Well, of course, in this case, I want a series to begin with. But where in the world is the series? I don't have one yet. So let's go ahead and create it. So public, let's say in this case static, I'm going to say IEnumerable. And then, of course, in this case, I'm going to create an enumerator for the int itself. And I'm going to call this as series, if you will. And what does the series do? Well, I'm going to say count is equal to n, whatever that value of n potentially could be. So in this case, I'll say a number is n that I want to start with. Then I could say while true, and then I could say yield return. And then in this case, of course, I could return, this is count plus plus, and I could start returning a number in the series, if you will, starting with this particular number or the value that I'm interested in returning. Well, then, of course, once I do this, I got a series on my hand. I can start with the series, but then I can say dot where, given a particular number, I want to say number mod 2 is equal to 0. And of course, I'm asking it to extract only the even numbers. I don't care about anything else. Then I could do a select. Given a number again, I can say math.square root of that number, and I can return a square root of that particular value. And then finally, of course, I can say take, and then give the value k that I'm interested in. And of course, this will start with the value n that we were supposed to start with. So n is equal to, whatever the value is. My memory is so wonderfully flawed, as you can see here. Well, the value n is 72 over here. So let's say 72. And then, of course, int k equals 219 that I wanted to use. So we could say those are the values that I want to work with. A little different here in C# than we saw in Java, but a series is creating with a yield word, and it says I'm going to keep producing values along the way when you ask, if and when you ask it, and finally I'll perform a sum operation on the result and print it. So what we can do in this case, of course, is we could print out the result in the very end, ask it to perform the computation. So you can see that is a fairly simple equivalent of C# code to do almost exactly what we did in the Java side, and we got laziness in this case. So what we're doing here is the take operation is kind of like the limit operation you saw on the Java side. The take says only take k values out of this and not any more. Well, the evaluation of the enumerable is lazy, as you can see. It only performs on demand, and it evaluates as many times as you ask it to take the value and no more. So you can start benefiting from code like this, and you can have laziness being come into picture. So we can see how lazy evaluations lead to efficiency in code quite easily. Well, the point I want to really summarize this with is that one of the really big charming features in functional programming, if somebody comes to you and says, what's really cool about functional programming? or what would you really tell them as what is charming about object-oriented programming? So when somebody says, what is really big deal about object-oriented programming is, I'm going to say object-oriented programming is really all about polymorphism. So isn't that true? Because what you really are after in OOP is polymorphism. Because if you don't have polymorphism, because polymorphism gives you extensibility of code, you can call a function, but the actual function that it will evaluate is not known to you at compile time. At runtime, it will decide what the function is based on the runtime type rather than compile time type. So the most charming feature of OO programming is polymorphism. There are a good number of object-oriented programming languages that don't even have interfaces, that don't even have inheritance, but all of them have one thing in common, which is polymorphism. Well, what about encapsulation? Well, encapsulation is extremely important. What about abstraction? Oh my gosh, it's extremely important. But they really are after one thing. Encapsulation and abstraction really provide polymorphism to us. Without encapsulation, you cannot attain polymorphism in OOP. So the real most charming feature of OOP for me is really polymorphism. So I'm going to say a lazy evaluation. So lazy evaluation is to functional programming as polymorphism is to OOP, because that is what we really are after. What are we really saying in functional programming? Oh, you better really honor immutability. You better write pure functions. You better really honor all these wonderful things. But often the question is why? Because what we really are after is efficiency that we get from a lazy evaluation. So to me, the real charm in functional programming is the efficiency we get from things like lazy evaluation. Of course, parallelism is also possible and makes it easy with immutability, but of course, things like parallelism and lazy evaluations won't be possible without purity of functions. But the real purpose of purity of functions is not because we want to be fancy about keeping functions pure. It's not a fashionable thing. The real reason why we go after those things is it leads to a greater good, which is lazy evaluations and potentially parallelism where it makes sense, and that's what we really are after. So that's really the charm in functional programming is efficiency through lazy evaluation. I hope you'll be eager to make use of laziness. That's all I have. I hope that was useful. Thank you. So the question is, I'll repeat the question. So the question is, what about resources for, in C#? Honestly, I had a really hard time getting my heads around functional programming. And I really finally decided to invest a lot of time in learning Haskell. And I failed 3 times doing it. And then I realized the reason I found it so hard to learn Haskell was I was approaching it the wrong way. I was getting really, wrapped around by the type information. And then I realized that Haskell actually is so wonderfully statically typed, I don't have to really spend my time saying the type information so much. But the point really is, learning Haskell actually made me a lot better in writing functional code in multiple languages, C#, Java, and so on. So the irony is, I would say, if you really want to get better at it, take your time to learn Haskell. And I go out to learn about languages I would probably not even use at work. And the reason I do that is because by learning those languages that I wouldn't use, I actually end up using the languages I do have to use in a lot better way than I generally do. So my recommendation actually is to go learn Haskell. And the reason I say that is, it takes you away from your comfort zone. You're thinking about it in a completely different way because you're away from your comfort zone. And then you end up actually using some design principles and patterns that you normally wouldn't. And then when you come back to the language you are familiar with, now you're thinking about it very differently than when we normally do in the constraints of the languages we do. One of the biggest constraints I see often programming in a language is I'm constrained by what the language already provides, and there are things that I can actually do in the language outside of what it provides in a very tactful way but I often don't even know that I could do that because the language has completely blinded me. But when I go use a language which is completely different, then I come and start tinkering with the language and say, whoa, I didn't realize I could actually do this. So that's what I would say is go, look at completely different things, and then maybe that will really change the way you think about and program in language. Other questions or comments? Yes, please.
I'm a glass half empty type of guy.
Start over the question.
Okay,
yeah, thank you.
So sometimes lazy evaluation can also cause you headaches, and if you're a C# programmer, like ReSharper a few versions back said, hey, change everything to IEnumerable, and then you can pass more things to your methods. And then immediately afterwards, you started getting all these warnings saying, whoa, you may be enumerating this enumerable 2 times, and whilst we're dealing with things that aren't coming from a database or aren't coming from files, you're good. But all of a sudden, when enumerating that enumerable is slow, you've now got yourself another problem.
Right. So that's a fair point. And one of the things I want to really emphasize is it often tends out to be a lot more than syntax. When we get into a language or a feature in a language, the first thing we come across is the syntax, right? Oh, we're trying to understand all these constructs and how to put them together. My argument is, almost invariably, we gotta have a really good command of the semantics of the language, because we don't really take the time to understand the semantics and the implications of a particular thing we're working with, a construct in the language. We could, A, get infatuated with ideas, which is not going to help us, or get drawn into certain code, not understanding the real implications of it, and then we end up facing some of these challenges as well. And so, in fact, a lot of ways, it's no longer what you see is what you get, right? It's a lot more than what you see that you actually end up getting. And clearly that's a departure from the syntax, because syntax often shows you what you are seeing and what you're getting, but semantics is often what you don't see, visibly in front of you. And I think your question really hinges on, hey, take the time to really understand the semantics, because semantics actually rules, right? Syntax becomes your muscle memory after a while. You're not thinking about the syntax after a while because it becomes your second nature to code with that syntax. The semantics is something you have to specifically think about every single time, because that's not something that you're going to see in front of you, but that has a very strong repercussions to what you do. So to your point, I would say, yes, you're absolutely right. It's important to understand the semantics, and then we can then say, here are tools I have in front of me, but the semantics tells me I shouldn't use this tool at this point. Maybe I should still go back and program in that imperative style in this case. And that's the beauty in language like Java and C#. You have the control now to decide when to use which. And I'm not suggesting functional is the right thing all the time, or imperative is the right thing all the time. I think we have to choose based on our current specific needs. And for myself, what I find out a lot of times is, I don't know how to do this in functional style right now, so I do this in imperative, but 3 weeks from now, somebody shows me a better way to do it in functional style, and it's often not the way that I thought I should do in the first place, but quite different from what I thought. But the beauty is, I can come back and refactor the code at the time to a much better style than I did. So absolutely, I don't want to let go of the performance and efficiency, and I can pick and choose what makes sense based on what I have at hand. Yeah. One more probably question before we wrap this up. Oh, all right. Well, thanks for coming then. I appreciate it. Thank you.